For more information on tutoring, personalized video solutions, or how to support Moof University and the production of more videos, check out moofuniversity.com. Thank you and enjoy. So next up, we've got covalent compounds. Now, covalent compounds form when atoms of different elements share electrons. Okay, and these electrons are specifically shared between nonmetals. Okay, so in a covalent compound, we'll have a nonmetal bound to another nonmetal. Okay, so let's start with an example. In fact, let's start with the simplest example of a covalent compound, and that'll be diatomic hydrogen, H2. Okay, so two hydrogen atoms coming together and forming a covalent bond. What exactly is happening? How does that situation occur? How do these two separate atoms end up sharing electrons? Okay, well, let's imagine it here. We've got a hydrogen atom over here, a hydrogen atom over here, with their electron configurations being 1s1, meaning that they have one electron. They also have just one proton. They have no neutrons. So there's the proton and an electron. We'll call this one on the left HA, the one on the right HB. Okay, so let's reveal their electrons because I haven't drawn them in there. There they are. Okay, so what's going to happen is that they're going to move closer together. Okay, they're floating in space initially. They're going to move closer together. Why are they going to move closer together? Well, because we've got a positive charge here in this proton in HA and a negative charge here in this electron in HB, and they're going to attract each other. Okay, likewise, the same situation will happen between HB's proton and HA's electron. Opposite charges will attract. So that's going to draw these two atoms closer together. Okay, so HA's proton will attract HB's electron, and HB's proton will attract HA's electron. Okay, and this will draw the atoms closer together. Okay, and so now we've got a situation where they're a little bit closer together. Okay, let's reveal the electrons there too. Okay, now notice the electrons are kind of moving down this way, right? Sort of towards the direction of the proton that's attracting them. Okay, so I've kind of drawn them in a little bit. Okay, they're here now. So this is it's moving closer to this, and this one is moving closer to this. Okay. Okay. Now you might be thinking, wait, if this is happening, that means that these electrons are getting closer together, right? And so are these protons. That can't be good, right? Because like charges repel. And that's true, okay? So there's an attractive force between the opposite charges, but there's a repulsive force between the like charges. So we just said that HA's proton attracts HB's electron, and HB's proton attracts HA's electron. That draws the atoms closer. But at the same time, HA's electron is repelling HB's electron. And that's not the only repulsive force, right? These protons are like charges. They're going to be repelling each other as well. So HA's proton repels HB's proton. Okay, so there's the attractive force, right? There's the attractive force between the opposite charges, right? So that's this right here. These are the attractive forces. And then there are the repulsive forces. So if I can fit this here, repulsive forces. Okay. So what happens is that the attractive forces, of course, are drawing the atoms closer together. But these repulsive forces are doing a certain job at repelling the like charges. What's going to happen is that they're not going to stop just there, though. They're going to get a little bit closer. Okay. What's going to happen is that we'll have this situation. Now the electrons are super, super close together, right? And we just described these attractive and repulsive forces. And we think, man, these electrons here, they're really close to each other. They'd repel. That's not good. And these protons are close together, and they would repel each other. That's not good. But there's also the attractive forces, okay? So I kind of want to show you guys this. So there are attractive forces between the opposite charges, which I'll reveal here as these little blue lines. So here we got a proton and an electron attracting each other. Here we've got a proton and electron attracting each other. same thing here, and same thing here. So those are all the attractive forces, right, between opposite charges. But there are also repulsive forces that we talked about. This here is representing the idea that these protons are repelling, and also these electrons are repelling. Okay, but the sum of these forces keeps these two atoms, HA and HB, at a sort of optimal distance between each other. Okay, there's a sweet spot where there's like a balance between these attractive and repulsive forces. So the atoms are close enough to each other where they like to be, but far enough from each other where they also like to be. They're not too close, they're not too far. There's an optimal distance between the two atoms. Okay? And the reason why this is good is now both HA and HB feel like they have a second electron, which makes sense because now they feel like their electron configuration, which I'm just going to abbreviate as config, is 1s2, which is the noble gas configuration of helium, right? So each of them feels like they have 1s2 and 1s2, right? Even though there aren't 4 electrons, but they both feel like they have a second electron, okay? So they're sharing electrons, right? They're sharing the electrons. And when we have this, when we have HA and HB sort of together like this, with these attractive and repulsive forces kind of all working together, we have now, instead of 2 separate H atoms, we have H2, diatomic hydrogen, which is called a molecule. A molecule is a unit of matter in which 2 or more atoms are held together by covalent bonds. So what we're showing here in this little drawing is a covalent bond. In fact, often it'll be represented like this. We'll have like H with an electron, and H with an electron over here, where that little dot represents an electron. And when they come closer, they end up being like this. We have 2 H's, and there's 2 electrons between them. And oftentimes, that's simply represented by a line to indicate that that's a bond, specifically a covalent bond between 2 hydrogen atoms. This concept here is sort of a sneak peek at the idea of Lewis structures, which I'm not going to talk about now, but we'll probably see more of that later. Okay. Okay, cool. Let's move on a little bit. So I just mentioned H2 as an example of the simplest covalent compound, but a covalent compound is just any compound that has 2 nonmetals combined, right? So here are some other examples. We have HCl, just the hydrogen atom and a chlorine atom, right? And they're going to be sharing electrons here, right? That's a covalent bond there. I haven't drawn the electrons explicitly just for the sake of space, but there are going to be electrons there. Here, H2O, water, there's going to be 2 covalent bonds, right? There's going to be a bond there between that H and that oxygen, and a covalent bond there between that H and that oxygen. And O2, we've got 2 oxygen atoms, 1 covalent bond between them, where they're going to be sharing electrons, okay? Now, each of these units are called molecules. These units are molecules. What's important to realize, super, super important to realize, is that each of these molecules is a separate entity. Okay, you can have one single O2 molecule. You can have a single H2O molecule. You can have a single HCl molecule. Now, this is important to realize because this is different from an ionic compound. Because ionic compounds have formula units, and a formula unit simply gives you the ratio of ions in a crystalline ionic compound. There's no such thing like as an ionic molecule. NaCl, for example, is not a molecule. NaCl just tells you that if you have a sample of sodium chloride, NaCl, that's telling you that for every 1 sodium ion that you have 1 chloride ion, right? It's not necessarily that you have just 1 sodium ion and 1 chloride ion. Whereas with molecules, this is just 1 molecule, right? O2, that's 2 oxygen atoms bound, and that is a separate entity from any other O2 molecule. Okay, I hope that makes sense. That distinction is important. Okay, now there are situations in which a small group of atoms can be covalently bound while being part of an ion altogether. In that situation, what you have are polyatomic ions. Polyatomic ions. Poly meaning many. Atomic referring to atoms, right? And ions, of course, referring to ions. So you have many atoms all combined together, but overall they have a charge, right? So here's an example, CO3, 2 minus. This is called carbonate or carbonate ion, carbonate. And so we've got 1 carbon and we've got 3 oxygens. And overall, that whole situation has a charge of -2, right? And many polyatomic ions, in fact, most of them that you'll come across are going to be anions, right? They'll be negatively charged. There are a few, in fact, I can only think of a couple, that are positively charged. One of them is NH4+, which is called ammonium ion. So ammonium, okay? And there's 1 nitrogen and 4 hydrogens, and overall they have a +1 charge. Okay, so these are examples of polyatomic ions. These are not covalent compounds, but because we have nonmetals bound together, right, those are covalent bonds, okay? So we'll have covalent bonds between these nonmetals, but overall, the overall charge will be, there will be an overall charge. So it's not a neutral compound. That's why they're called polyatomic ions, okay? Hope that video was helpful. Thank you for watching. If you found that video helpful, don't forget to like, comment, subscribe, and share with friends. Thank you and happy studying.